Okay, so this is the last video in chapter 8, and the last video is about an interesting example. So this is, I taken this result like a prediction from CNN from in 2012 presidential election. By the way, I want you to update the this example with a more recent election prediction, but somehow after this there was no like simple and clean example like this. Maybe prediction becomes more trickier, so maybe like journals do not publish simple prediction which is likely to be wrong anymore. Maybe that's my guess. So I cannot update the this example since then. So I will try to find it maybe after the next election. Okay. Anyhow, so let's see. In 2012, the two major candidates are Obama and Romney. Like so, simply, I will focus on Obama's percentage. So 50% of survey respondents said they support Obama, right? And that is simple. This is point estimator, but also what it says is in a fine print, the sample size is 783 likely voters, and the margin of error is 3.5% points, right? So these two are more statistical, information. Also, what's missing actually in this graph is that there is no like a confidence level, right? Confidence level should be given, but it is missing because it is the standard. Confidence level is 95%. And that is the standard, so they did not say that. Okay, so I'm going to use this as an example as a last example of estimation. Okay, first thing we need to think about is its binary structure. So underlying distribution is binary because if you choose a random voter, then the result is 1 or 0. 1 if he or she supports, say, Obama in this case, or just a candidate, and 0 otherwise, right? So it is binary from a candidate's perspective. And then the parameter we are interested in is a probability of success. I'm going to call this success, right? So probability of 1 is the parameter we need to estimate. But remember, what we have studied was about the population mean, and and in binary case, mean equals the probability. So we may apply our procedure, our method about the population estimation of population mean in the same way for this probability. Because probability equals the mean, so estimating the probability equals estimating the mean. So we may use the same estimation procedures. So that's why I said estimation of the population mean is widely applicable to many other cases. Anyhow, so we justified the formula. The formula we derived applies to this probability estimation. Okay. Another thing here is when you have a binary distribution, now maybe you must be familiar with this formula. The variance follows from the same parameter, right? So there is, you remember the variance of a binary distribution is p times 1 minus p. So the standard deviation should be calculated from this formula, right? Right? So you don't need on any other information. There is no information about standard deviation, but that's okay because you can calculate that from the probability. Okay? So then let's see what we do. So let's think about a different example for simplicity. So suppose that you are like a political research institute. You are predicting the election. So you did your own survey. So you surveyed 400 voters, and somehow 320 of them support candidate, the candidate you are interested in. Okay, and how can you make a confidence interval with 95% confidence level? The answer is simple. You just need to use this formula. So you need to find four numbers. Sample size is obvious. That is obvious. And this is also obvious. You know how to find this number. Then the problem is the sample average and the estimator for the standard deviation. How can you do that? First, the sample mean equals the sample probability of success using the binary structure. So then out of 400, 320 was success. So the percentage is 0.8. That is the mean, right? Remember, the probability of success equals the mean. So anyhow, 80% is the mean. The point estimator is calculated this way. And standard deviation, you need to calculate the standard deviation from the binary distribution formula. In this formula, the P, the probability of success in the sample, is 0.8 as we calculate here. So use that in here, right? And you will get 0.4. From your sample, you will get a standard deviation of 0.4. So I chose the number 0.8 so that the standard deviation is simple number. And sample size is known. And for 95% confidence level, we know we are going to use 1.96. So you get all the four numbers. The only difference is this one because we have binary. So it's actually simpler. You don't need another standard deviation, but just use the sample mean in this formula. So it's simple. Then you will get a margin of error like this. 1.96 times standard error, standard deviation divided by square root of n. So you will get 0.0392, which is 3.92% point, right? So average was 80%, but you have to plus minus 3.92% point. So in the end, based on this data, your confidence interval is between 76.08% up to 83.92%. So that is the interval, like plus minus, like around 80%. Okay. So then the question is, okay, we just did 95% confidence interval, but you don't like this margin of error. Margin of error is too large. So usually in this prediction, we use 3.5% point. I don't know why. So this is a common margin of error in this kind of election prediction things. So then let's follow that standard. I'd like to lower the margin of error to 3.5%. Then how much sample do you need? We are going to do the same thing. The margin of error, this guy, must be smaller than or equal to 3.5%, 0.035. Okay? This is what you have. And we know number here, 1.96. And standard deviation, the same. And you only have n as an unknown. So from this inequality, rearrange and square so that you get sample size should be greater than something squared. Calculate that, you will get this number. So that means to reduce the margin of error to 3.5% standard, you need 502 observations. You have to do more survey, and then you will get this much margin of error. Okay? This is how we design survey. Okay, now it's your turn. Think about another data. You ask 400 voters, and 200 of them support the candidate, and then find the margin of error at 95% confidence level. Right? Pause and do the math. Okay, so let me show you how to do it. So when you calculate the margin of error, remember we are calculating this guy, and this part is the same because same 95% confidence level. Sample size is easy, and the standard deviation should follow the binary formula. So then plug them in there. So z value, this is 1.96, no difference. Standard deviation is calculated following the formula, but now 200 out of 400, 200 successes out of 400. So success rate is 50%, 0.5. So you plug in 0.5 here, then you are going to get a standard deviation of 0.5. Okay, and then sample size 400, the same thing. And then as a result, the margin of error is 0.049, which is 4.9% point, right? So because the probability change it, the margin of error change it, right? And as before, it is too large, larger than the standard. So I'd like to make the margin of error at most 3.5%. Without changing the confidence level. Confidence level is also following the standard. What is the minimum required sample size for the margin of error to be 3.5%? Calculate. So the answer is like this. So 95% implies 1.96 does not change. Standard deviation does not change, but sample size is remain unknown, and it should be smaller than the desired margin of error, 0.035. So this inequality implies this equivalent inequality for n. Sample size must be greater than this number. So it means you need 784 survey respondents. So, right? And then back to our original thing. You see the similar number here. This survey is based on 783 voters. It is different, a little bit different, but I guess the difference is coming from like maybe decimal errors. It could be like not exactly 50%, maybe could be like 49.6% or 50.3%. So maybe I think somewhere rounding error have occurred, so it causes a small difference. Anyhow, you see this election prediction is based on exactly the same framework we learned in this chapter. Okay, so as I said, I want to update this example to a more recent election, but there is no more clean example like this, right? Okay, this is the end of that example. And before finishing the video, I have a small comment on I receive a lot of questions from students who learned statistics somewhere else. I know that you learned statistics maybe as an AP course or before you transfer, or if you are a transfer student, or you may have taken like a statistics course from other majors. Like I understand, yep, but so basically topics are similar, but details could be different. One of the key difference would be something like this: students' T distribution. When I was a college student, I had to learn this distribution. Somehow it was the standard at the time, but not anymore. So many textbooks have two separate chapters: interval estimation for the mean. So this is basically what we are doing. Interval estimation for the mean. That is what we are doing. But they discriminate two cases: when the standard deviation is known and when it's unknown. Right? Theoretically, they are different. If sigma is known, you may use normal distribution. If sigma is unknown, usually it leads to student T distribution. But the difference is different. The reason why it is different from me is because they don't use the central limit theorem. I am teaching a more advanced, more contemporary statistics based on the central limit theorem approximation. this makes more sense these days because these days, basically the data are bigger than like 20, 30 years ago. So having, like say, several thousand data is not a big problem these days in many cases. So that means the approximation based on the central limit theorem works much better, right? So, and computing power is much better now, so we can handle that. So what we are doing these days is not using these two cases, but just approximate everything to the normal distribution that will unify all these methods. So let me explain. So student t distribution requires very strict assumptions, like the single outcomes distribution should be normal. Already it is pretty tough. For example, if the underlying distribution is binary, it doesn't work. Our method does not work. Like presidential election cannot use student t distribution. Good thing is, if this assumption is correct, then it is not an approximation. It is exact distribution, but that is theoretically nice, but not that useful because you don't know if the underlying distribution is normal or not. Instead, what we learned is, what I teach is based on the central limit theorem. I don't care what is the underlying distribution. I know that the sample average will be, in the end, the normal distribution, right? As long as the sample size is large enough. So why don't we use normal distribution under, like using with, if the sample size is large? So that is enough, and it is approximation, but the error will be pretty small. So this is my approach. So in case why what you learn here is different from what you have learned elsewhere, then I will tell you this. I'm sure that this is more practical, more useful way to estimate and calculate probability, normal approximation based on the central limit theorem. This is more like, advanced. I mean more. How do I say that? This is more trendy approach. So this is the only thing you need to know in this course. Just in case, still there are some remainders from t distribution. For example, we usually denote this guy as t. After standardization, like subtracting mu and divide by square root n, sigma square root n, we call this t statistic, following the name of t distribution. So now, when I was a kid, when I was a college student, we learned this follows a student t distribution. But what I teach is this follows normal distribution, approximated to normal distribution. So I believe the textbooks need to be changed, need to be updated, right, based on normal distribution approximation. Finally, this is the difference between standard student t distribution and normal distribution. Blue and orange, I don't know what is what, but I wanted to show that student t distribution is not much different from the standard normal distribution. Basically, you can approximate student t distribution to normal distribution even when the sample size is small like this, right? It's not that much, not that big data. Still, approximation error is pretty small. Okay, that's it. Thank you for watching, and I'll come back with hypothesis testing in chapter 9. See you later.